day we have a round table. Contrary to what is written in the program, it will be in English because we have several non-French speakers. So we have 6 people all together at this round table, and so 3 of them you know, so Eric Drager, Mitsui Sasato, and Thomas Schultes, because they have given talk this afternoon or this morning. And then we have 3 additional participants. So we have Virginie Grand-Girard from CA. She's a applied mathematician, computer scientist, and she works on a large fusion code, tokamak fusion. The next person here is Isabelle Terras from Airbus, in charge of at Airbus of research and development. And Gabriel Staffelbach, who's worked at Fairfax and is a specialist of combustion code and working on large code in general. So we have 3 users in addition to the 3 speakers, and 1 user, Virginie, more on the research side, 1 user, Isabelle, which is more on the industrial side, and Stéphane, maybe you're in the middle, because at Fairfax you're a bit making the links between research and industry. And so the thematic of this roundtable is a roadmap to new architecture, how to develop software on the long term to use this new architecture. So maybe since we didn't have hear a lot about it during the day, maybe we could start with Isabelle, saying us what is the view of an industrial to the view and the outlook toward using this large computer in the future for industrial usage.
Okay, thank you. Of course, we have not really a roadmap on our own to go to the new architecture, because we are building a plane, a satellite, etc., aircraft. Not really a computer, but we have a huge legacy code also, like CEA. Because especially in space, we begin simulation in the late 80s, early 90s, starting, of course, in Fortran, full Fortran. We do not have enough workforce to refactor all our code. So we have taken some priority, and Cron Jewel, as was shown by CEA, we have invested. That means that there are 2 kinds of investment. One is the human one, the fact that we need a team, and this team need also every 7 years to have a newcomers in order that we can handle the ball to the next generation. It's very important to find those kind of people. And the second one is also to take some risk. And for example, we invest in the runtime middleware in order to know what are to be prepared to the new architecture, because we have no weight on the market to define what will be the next big computer. It's a risk because there is not standard for the moment, and we are very eager to accompany what we big challenges like we have seen by the Europe, because we know that if a wide community coming from academia push to go to exascale, then some standard will come, and we can have them. And especially the ISV could also put them in their code, because most of our codes are also commercial software, because we need some kind of traceability, we need a kind of industrialization. And we find that they are not investing too much on the HPC part, because it's a niche. A lot of things are niche. And I think that the standard will come from your community.
Okay, thank you. Maybe Gabriel, you want to comment on industrial code, but which are more in the hand or close to the research community?
Yeah, thank you. Well, on our side, we're exactly in the middle between academia and industry. So exactly what we are doing is trying to industrialize research codes for industry, and so they don't have to rely on ISVs, in fact. So it's exactly the problem you were mentioning, trying to certify these codes, trying to make them the rigor so that they can give the same results when you change the approaches. And this is a major issue we have right now. This takes a lot of time, and when you refactor a code, it's something that's totally forgotten. You write a new code, say, okay, you have a new physics, but it actually needs to do all the physics that it did before. And this is something that nobody actually pays for it. So this is something really important. Also, well, the thing is that, as you mentioned, standardization, for us, it's also useful for another thing, is for people. Because if you code with standards, you don't have to train them, because they can just get the information from websites and so on. If you start to use your own DSL, your own programming models, or special things like C++ 17 or something that are still not really completely mastered, you need to train them for 1 year or 2 years before they are fully operational. And for us, it's not viable. People at Fairfax stay 2 years, 3 years on a PhD. So this is on our side. We are able to use academic codes and send them via HPC to industry, but we need to rely on robust and standard programming models. And you mentioned runtimes, for example. This is something that has been around for quite a while now, but there are so many, and every time you ask the people that develop them, theirs is the best. But the real comparison is actually never done. And this is something we don't have also the way to say to people like, okay, just use OpenMP5, finish OpenMP5, and we can use it. So it's a really big problem for us to switch from language to language, but we do it, actually. We try it, and I think it's what we have seen today is that everybody's trying a lot of languages, and the solution doesn't exist yet, hopefully one day. But the idea is to try. And the main problem actually for us is the people, as was said in the previous presentation, people that want to try it and that can actually use it.
Thank you. And maybe we can go to Virginie. So Virginie working in fusion, so there are huge advancements in many projects, but particularly in the ITER project. And simulation is, of course, key for ITER and require extremely large resources because it's a kinetic code that you need with 5 or 6 dimensions. And it's also a long-term vision because ITER will be running in several years from now. So Virginie, can you comment on the software development and the software roadmap to go along with the ITER project?
Yes, maybe something that has not been discussed for the moment here is for our code, we already use the petascale machine. So for Gisela, we need almost 100 million of hours per year for the simulation. And we already have a problem due to the fact that we have to address different architecture. We use GNC machine, we use also Prace machine, and each time we have to change the machine, and we have to port the code on the different machine, and it is already a lot of work. At each time it requires 1 or more months to try to have the same performance than before, even trying to have better. So I think it's already a issue that we have for the moment, is the difficulty to change to the different architecture. And as Edouard has already said, to address ITER simulation, we already know that we will need exascale simulation, so we prepare the code we try to prepare the code for that. And a first thing that we see is that if we want to address the new architecture, we want to use the new software for that, for instance, like Cocos or this kind of library. The problems that we face is that they are more developed for C++ language, and the code is written in Fortran. So we had in mind to rewrite from scratch the code to write it in C++. But the problems that we face, in fact, is that the code is a research code to do physics, The first job that we have to perform is to add new physics to try to go to more and more realistic simulation. So 80% of the time that we have to spend for the development of the code normally is to improve the code to add more and more physics. And the problem is how you can do to rewrite a new code from scratch, knowing that Gisela is developed since 15 years, and at the same time trying to continue the development of the current code. And it is one of the points that probably we have, and most of the research code have, is that it's not a fixed code, and it's always in development, so it's very complicated to do both.
Okay, thank you. To follow on this development, so we have seen in all the talks that the trend is more to have a kind of a separation of concern and trying to abstract the hardware by putting some complex software layer. So maybe all of you could comment on two issues. First of all is how can you really abstract the hardware, and how can you be ignorant of the hardware even if you do high-level physics? For example, we had example with the Monte Carlo code, and you have really all to reshuffle the algorithm to be efficient. So how can the physicist be ignorant of the hardware? And also this software technique to abstract the hardware, they are very sophisticated. We talk about template programming, things like that, and don't you risk to lose the users or even the physicist programmer by using such advanced techniques that are not mastered by many people? So anyone who can, yes, Sato?
Yeah, first of all, don't you worry about architectures. So our machine is supporting the conventional programming model. Okay. You don't have to write any code.
How much time do we get on that machine?
Huh?
How many hours can we have on that machine?
Oh, it's already come. We have already chip, and so it's ready to go.
But you said the next one would be accelerator,
okay.
so we are all afraid now.
Let me talk about the next machine, next architecture. So at the last of my talk, so I say that if we are going to increase the efficiency or the performance power, so we need some specialization for some accelerators. But it's not necessarily for about the GPU, I think. So is there many ways to accelerate the computation? But the problem is that that kind of the specialization can be shared by the many users. So that is the economics, I think. So, and another thing I'd like to point out is that according to our result, so within the nine target application, the 4 application is just only 1 pipe is enough. So that means that we don't need not so much the floating-point performance, at least the existing application. So that means that that many people is taking a look at the props, but also the next machine will support more memory bandwidth to support much efficiency and more efficient computation.
Actually, I was going to ask you a question. Are you saying the next machine will be accelerator, but will still be the same architecture?
Same what?
Well, the point that, you know, as we go from single core to multi-core, hyper-threaded multi-core, we have actually changed the architecture. As we go from multi-core, many-core to GPUs, we have again changed the architecture. And while it is putting people under pressure because they have to adapt code to new architectures, NVIDIA GPUs they come with a complete software stack and the programming model. When multi-core came, they didn't come with a programming model. Yeah, at some point later, we had OpenMP. But OpenMP there are a lot of dangers with OpenMP that are pushed under the rug. In OpenMP, you are duplicating the code. You have the same semantics implemented in a serial code, in a loop nest, and then annotated with OpenMP. How are you going to make sure that the two are in sync? Because you said the code is being further developed by physicists who we say should not worry about architecture, which means they should not worry about the OpenMP statements. They should just continue their code. And then who is keeping the OpenMP in sync? So we are putting a blind on us, or basically we are closing our eyes with OpenMP. I fully agree with the things Jesus was saying about giving hints, using a task-based approach. But OpenMP is the wrong language to do it, because what you're doing is you create more and more code that now duplicates something you learn should learn if you ever take a programming class, is you should never duplicate code. So we are creating an unmaintainable stack of software. And I'm asking again, is your next machine going to be the same architecture as Fugaku, just that you call the processors accelerator, or is it going to be a different architecture?
I'm not responsible to answer that question, but so my idea is that the architecture, one of the choices of the architecture is that the GPU type of the accelerators of an arithmetic unit can be embedded in a CPU, and each core have such kind of arithmetic unit. And to program for that, that you can use the shared memory, and also it can be the program by the secure or GPU type of the currently GPU type of the programming model can be used for programming for that kind of type of architecture. That is one of the example, I think.
Okay. Maybe Rick want to comment on OpenMP, since it's highly pushed by the US and as a programming model, OpenMP5 for accelerator architecture.
I think what you said is absolutely right. It's not. You can't just fix all your problems by decorating your loops and calling it good, and there's a lot of duplication that comes. But there are cases we've seen where, because of the portability, especially if you're using Fortran, you don't have many other options for a portable approach. So people are using it because there isn't another widely adopted standard. And I mean, we could maybe push OpenMP to a place where it solves things better, or maybe we need to find another markup language that's better. But for non-C++ languages, we're seeing it as kind of our best choice right now, and that's mostly because of a lack of other options that have portability.
So I think what will have to happen is there's a tool change. There is C++ that is evolving rapidly, and this is, thanks God it's C++ and not Java or something else. It's something that you can use for performance. There are things evolving in the standard that are going to make even the meta-programming in C++ much simpler, in C++ 20. So there are actually a lot of good developments happening there. And I encourage people to really consider that very, very carefully. I wish Fortran would do similar developments. There is just not the same, economic power behind Fortran. And so what could happen is that we have things are based, say, on compiler frameworks like LLVM, but there could be others. I'm not trying to advocate one particular, that are open, languages that keep up with the architectural developments, and that's really happening in C++. So the goal should be to have all these new architectural developments like the CUDA model eventually go into C++. It will be CUDA, and then others will call it differently, but it will still be CUDA. that eventually goes into the C++ standard. And what I'm really asking the community and also the software developers is you may use OpenMP and OpenACC to try new things, but the old things, how to parallelize a loop, that you should write in Fortran 18 or in C++ 17. You should not use the OpenMP markup for that. But those who fund those projects have to know every line of OpenMP that you write will have to be cleaned up by somebody later, or you will have your viscosity will go up through the roof.
Yeah, I agree completely with what you're saying, but this is, I think, an architect point of view, where you say, okay, I use the latest language that
I'm
is
not
the
an
most.
architect.
No, I mean, it's their point of view, maybe. Yeah? But you use the latest language, which is quite adapted to the architecture changes. However, for legacy codes, is a big problem. Because you cannot write, say, okay, we want to write our code today with C++ 17. There's already 20 that is around the corner. And rewriting our code is 1, 2, 3 years minimum. Of course, you can modernize by steps. Okay, it's not that's not a question. But for me, this pushes the complexity to the developer part, saying and try to use the language on the developer side. I think that we need to separate. This is the same problem I think that Virginie has. Is that our researchers are not computer scientists. Yeah? And so we need to separate, I would say, the layers with maybe different languages. This is a debate that is quite complex, but yeah. And that people can work on their layer with the language they're more familiar with. And you can modernize bits of it, blocks of it. And it's a bit what you can see with the approach that Raja did. Raja, they divided the memory management, the runtime, and so on. So these blocks can be actually modified separately. And in the codes that we are using, this is not possible because Fortran was not built like this. But I think new codes should be built like this. Maybe first layer in Python, for example, because most people know that. And then the performance part and the really basic blocks executed in C++ 11, STLs or something that, as you mentioned, do not require complete changes every time there's a new architecture or a new pragmas. Because I do agree that the pragmas is the worst case scenario, but it's the only case scenario we have today for Fortran codes.
But to be honest, I don't like C++.
Yeah.
So recently I'm working on a C++, but this is I feel that C++ is a kind of the new Fortran. So that is because of course I like that I support the DSL. So DSL is a good idea, but designing DSL by using the C++ template. I'm a little bit afraid of the complexity of the implementation. So if the application people is writing the template library, so got an error. So I think maybe he or she programmer doesn't know what they can do. So of course the expert of the C++ programmer is good, but what I would like to say is that if you support the DSL approach, we need a more sophisticated the language framework for the metaprogramming.
In this point, you're right, that the traditional template metaprogramming is we have done it, Raja and Kokos are now repeating it. The effort, you get into a software where you cannot scale in the number of programmers because the fraction of programmers who really know C++ template metaprogramming is very small. And there are companies, I think Google also, that actually don't allow this type of programming style. But this will become easier in C++ 20. when concepts become first-class citizen or not some implicit property of a templated code. And so that is one thing. And the other thing is the approach that we see that is used in machine learning, where you have domain-specific languages and libraries that you use in Python with the toolchain, as I tried to explain behind it. So the many parts of this toolchain that you need actually exist today, even in the open source. And one is this multi-level IR that Google is developing. So those things exist and can be used. So domain-specific libraries can be simple for domain scientists to use, but you will still have to maintain these libraries and languages. And the basic message is software is not cheap. Software is an important part of your system, and you have to invest in it, and you don't do it once. As you develop the mathematics, you have to develop the software. Because software ultimately is starting from the top when you write equations, all the way to digitized algorithms. Everywhere is mathematics, and you need, some can be supported by systems, by other automated systems, but a lot of it, there's always a 10 or 20% part of it that you need smart people to maintain. And those are software engineers and application developers, and they will never go away. They need to be around, and you cannot say, oh, we have now this code and we're done investing in software development. That's like saying, I have this airplane and I don't have to maintain it anymore. Actually, it's even worse than just maintaining an airplane.
So what you're saying, basically, of you, is that C++ or any flavor is a good way to go, but it's extremely complex and you're going to lose the user in translation. Then Fortran with Pragma is nice, but it's driving you to a dead end, basically. So above the cliff, so you need some kind of a layer, and then C++ or something else underneath to.
So I think the viable solution today is with Python or Julia on the top as a user interface to the scientists, domain scientists, but even then you need to maintain the DSL in Python, and you need to maintain the toolchain. Again, I repeat what I just said, the infrastructure to maintain the toolchain is actually becoming more and more available. And so it's a cost that you can eventually calculate, but you will not be in a position where you can just write in Python, not know what you do, not worry. Nobody worries about the hardware. I'm not saying everybody has to worry about the hardware, but you have to have the know-how about the system and the software systems underneath in order to engineer an entire solution that works. And there are organizations that do this. So, for example, ECMWF is maintaining a substantial team of people that maintain both the data and the simulation software, and are capable to move things forward. So
a lot of manpower needed.
But it's a lot of people they have to maintain, okay? And we, the rest who is consuming from ECMWF and all the weather services that invest in ECMWF have to know there is a big cost that will never go away, that we have to maintain.
So what we see is that there are a lot of people that are in the loop. You have the application domain, you have the mathematician, you have a computer scientist, you have people more specialized in HPC. And I think that when we saw the cost, the Center of Excellence, I asked the question, we see HPC capability everywhere, but I think that it is exactly what we need. That in the area, there are the people who is mastering the physics, the application, because it may not be exactly the same people. The one who master the equation, the model, etc. And then you have the one who will maintain this layer, as you said, that the one who know about the plasma, etc., the astrophysics, what you want, should have really a language simple, and I think it's mostly Python now, because young guys now are trained in it. So they know to use it. And then after, you have someone who know the application, but also the software that can maintain and make evolve the things, but also have the link with the one who know better architecture and what is really the layer, the very low layer, which will be in the right language to be efficient. And I think that we really need to build those competencies by people working together, because nobody can now handle the complexity of the problematics.
Maybe if there's any question from the room, we can take a few. Yes, Michel?
What we're seeing here is really quite interesting. It comes from what I would call large organization with structured organization and people. Okay, say again. Thank you. All of you probably belong to organization with dedicated resources. It may not be easy, but the resources exist, that you have some way of setting things up so that people will work with it. At the other end, there is research groups which are much more loosely organized with people who have quite different skills and basically don't have the resources to have such a nice way of setting things up. How can they survive in this very difficult environment, ecosystem?
They die.
I don't know, maybe, yes, for instance, in our team, 80% of the person are physicists. And I agree with all what you have said, but problem is how you succeed in developing a new code in C++, knowing that these persons are not able to change from Fortran to C++. So in the real life, I think it's more complicated than that. I think most of the applications have the same problems than us, that yes, we have to go to the best language to address the new architecture. But in reality, what we see is that we have already had a lot of problem to go from Fortran 77 to Fortran 80. So when I discuss with the physicist and I tell them that they have to learn now C++, it's completely, it's not possible anyway. It has already taken more than 7 years to go from MATLAB to Python just for post-processing. So if I have to couple Python with C++, that means two languages, so it's very complicated. So.
You will not get, to answer the question, you will not get around. If you develop a complex numerical computational model and you want in the end to have simulations run at scale, you will not get around having an interdisciplinary organization with some structure, but modern software organizations can be organized agile, and the know-how how to develop complex software system is out there. The sad thing is that we scientists, and I say this as a physicist, think we don't need that, okay? And it just doesn't work. It's the same thing. You cannot understand physics without understand mathematics first, okay? No, that's just the fact that we all accept. You cannot do sophisticated computational physics without understanding software engineering. Or you cannot build sophisticated experiments in physics without understanding electronics. Okay, and I don't know why in academia we have the feeling, we don't need proper software engineering. And then maybe we will have a PhD student who did not get the proper training because we could not train them because we don't understand it. Do something that we don't understand anymore, but we see some good results. But this is not leading to a stable software framework.
Thomas, fully support what you said. It's a deep conviction for me what you're saying about software engineering. But I think there is also organizational and management dimension. As long as the higher level management doesn't accept to pay for the different skills, you might want to build a house or building without a plumber, electrician, and with a mason doing everything. It will not work. Or the carpenter doing the foundation instead of the mason, it won't work. You will end up with a hut in the woods in some cases, but you will not end up with a nice house or building. So higher management, our policymakers and funding agencies and organizations must admit that some things must be organized into projects and to estimate the necessary resources to organize things in a proper way, including software engineering, project management, quality assurance, verification and validation, and so on and so forth.
Yeah, but now let me give you just some numbers. When I came 10 years ago to CSCS, we were investing in the beginning about 10 million to catch up with TerraScale system at the time. But we invested about 20 to 30 million into a network of software engineers at Swiss universities. This is what you end up having to do. Now, is this what is happening in EuroHPC? I am very supportive of EuroHPC, and I find very remarkable the progress that was made in the last year in the joint undertaking with how they organize all these countries coming together, all these co-investments happening. This is all very remarkable, but we are totally lacking the investment in software. The centers of excellence is too little funding, too short term. You need a sustained effort that's at least, 10 times, maybe even 100 times bigger. Let's just try to change it. But the politicians also need to understand having a machine on the top 500 list, on the top of the top 500 list, is of no use if you have not made appropriate investments in software. And DOE is actually doing this now. Okay. Better,
We're doing better. We're still not all the way there yet. And we actually still have research groups like were described where the physicists want to do the physics. They want to just hack and jam it together so it works so they can get the paper out as quickly as possible. And you have to impose discipline from the top to keep that from happening. There has to be rules. There has to be CI servers and Git repos set up such that you can't just cram in whatever code you want, but it has to pass through rigorous standards before it can be put back in the common pool. And once you put those in place, a lot of times the physicists will work with that. But there's still always a very roll-up-your-sleeves attitude of I just want to get this paper out and I'm just going to hack the code until I can. And it's very hard to fight that.
Just one comment about what you're saying. I totally agree that you need to build kind of a group that builds on all the competence to do that. However, you need to avoid also the not invented here aspect of
Absolutely.
that. You need to build on communities that are large enough so that there's some kind of changes. If not, what happens with the Fortran code, that everything is in Fortran and no, Python, I don't care. So so this is something also a problem if you start training that you need to fund everything yourself. So you need to build also on the communities, and as you did with universities, that where you build on this, and they can also send the message to other places.
So in Japan, since the K-computer project, we have the same discussion. So we need some support engineer to tune the code or maintain the code or something like that. But we had a problem of the career path of such kind of engineer. So if we would like to exchange the people with the industry, but it's not so established the career path for such kind of person. That is our biggest problem for supporting the engineer for scientific application.
Yes, and I think that in a university or a research center, you will always prefer to have a position for a researcher than for an engineer whose job will be to help the younger, the PhD, train them to new language or a way of best practices, help them, and then ensure that the quality is okay, and put it in the data, in the software maintenance. And with this responsibility, we need those kind of people because it is not the job of the PhD to do it. Okay, and there are not enough position in the research lab because they prefer to have a researcher. So it cannot work. Huh?
So I think you made a very important point that, this not invented here syndrome. Communities can work together and share the burden of development. And this can happen at all levels. So we can have like linear algebra. There were days where people wrote their own matrix multiplies. At some point there was infrastructure that was developed, BLAS and LAPAC and now slates and so on. And this is what I meant with DOE, I think, is making a very remarkable effort now within the ECP to really bundle a very, very powerful set of libraries and tools and software infrastructure that I think rather than trying to now, it would make no sense to develop this from scratch here in Europe. We should collaborate with those projects to help maintain this stack. And maintain means also innovate on the stack into the future. And I think if communities form to do this, and we see much of that in the climate and weather community, I don't think they could operate this complex model they have today without having that discipline. So in some communities it actually exists. It should maybe be studied and transferred into other communities.
I think it's part of the main job of Center of Excellence. I think definitively it's what they have to address.
Okay, any other question from the room? So Gabriel is sorry he has to leave because he has an airplane, so he apologizes. So maybe because it's getting time to conclude, maybe we could try to give advice. If you have to refactor a code, a big project, what would be your advice to start, knowing that there is no perfect way and that resources will probably be limited? What would be the way to go?
I'm asking the question to the team now, so I have not exactly the answer. What we have decided in our case is not to rewrite from scratch the code in C++, but more to go to more modularization of the code with the idea to be able to plug kernel in C++ or C or Python. And I see probably is a good way because the idea is to keep just one code, the same code for the new physics development, and try to change part of the code step by step.
Yeah, I definitely agree with that. All I would add is what we have seen that has been very successful is wherever possible make the smallest proxy or mini app for it, and then really understand data motion, dependencies, the effect of different programming models, and basically exercise everything you can at small scale with the help from people who know the hardware well before you then refactor your big code. Don't just dive in and start changing things.
So I'm working for the architecture team leaders for the PostgreSQL project, but actually my background is programming model. So I think as Jesus said, the task-based programming model is the good way to exploit the new architectures. So they compose the program, the parts, and according to the dependency, the program is executed. So that is, I think, new ideas. So from the architecture side, so I really want to collaborate with the EPI project. So that is my conclusion.
Well, I think from our experience, what you need, and it doesn't contradict what was said or also Jesus said in his talk, you should try to identify regions of the code, and they may not be small. Like in the case of Cosmo, it was around 60,000 lines of code that were identified as this is the part that we really need to rewrite. But before you do it, make sure you put yourself on solid footings with unit testing and zero change testing. And then also understand exactly what Jesus said. You know, you need to understand from a mathematical point of view what you're doing from a data motion, or you know, you need to do your homework on what is your arithmetic density. You have to have a performance model of what you're doing to then develop a strategy on how you refactor, because there are many ways how you can refactor, and whether you do it in one language or the other is more or less a detail. In some languages it works easier than it in others. But you have to do this performance analysis and performance modeling work first. And once you have put yourself on solid grounds with test-driven development, and you have a good understanding of the performance model, then you should start working in the best language for the problem. And we started C++, we studied Fortran, Fortran 90, we studied C, C++, and we showed how we would do things in the different languages, and it was then our partners, Meteor Swiss and David, who decided we want to go with the C++ version. Even though it was not easy what came out, but it would have been much worse with Fortran or C. So that's the first step. But I think the most important advice I'm trying to give you is refactoring gets you on the train. But then you need to keep going on the train, and you will have to continue to invest in software. You're not done with it.
We have to work all the time. Please,
I will not give advice on it. We try to do it on several software. What is very costly is the validation, because we have a huge
Verification.
Yeah. And non-regression test, but sometimes you change also the algorithm because of the architecture. That leads you to change. First, we have put the frequency in the inner loop when we had the CRED. Then we had the SP2. We had to put it out. Then we had to put it back because we have multi-thread. There are a lot of things that are changing. That means that you cannot just verify that the digit is the same or not. You have also to see. Maybe sometimes the new result is better than the previous one, because there could have been a bug, or there could have been some approximation that was not seen at the time. So it's not only verification, it's also the validation of the result. And there you need an expert, not only an automatic tool that say digit is, all the digits are the same. And it's a human cost. So that's very expensive for an industry, because it's working only...
That's why I said you need to set yourself up with a proper testing framework, unit tests and zero change, because you need a test framework to be able to make your verification
So,
possible.
yeah.
Hopefully, the codes have been validated already. I know that this is probably in most cases not the case, and that we start with garbage, and unfortunately,
And with
you know,
garbage.
but that's a totally different problem. Okay, I don't want to get into that.
And the next challenge is also that we want to deal with multidisciplinary code, at least in our industry, with a fidelity that may not be at the same scale depending of the physics, to make a multidisciplinary analysis, then multidisciplinary optimization, that maybe that we will have a database model coming from measurement, some AI somewhere, and that we want to have the global performance of all the tools together, written in different languages, with different maturity and different performance. So maybe new architecture may be also a good thing for this, because with the heterogeneity, as we have heterogeneous application, it may help. But it's also the next issue. So if we lose time to rewrite all the small codes, all the physics, we may be late to go to this multidisciplinary goal.
Okay, thanks to all of you. So I think we have a lot of work to do, clearly, to maintain all our codes. I would like to thank all the speakers and all the intervenants at the roundtable of the day. I think we had a very fruitful and very interesting day. Thank you. And so, as you know, at ORAP we have a forum every 6 months. So the next one will be in April, 2nd of April, and there will be some work done here in CNRS. So the next forum, and probably the one after that, will be held at Maison de la Simulation in Saclay. And we will keep you updated. And if you're not, please register to the ORAP mailing list so that you can have all the relevant information. Thank you.
Yes.
I think